Hello friends, welcome to UGC EPG program. I am Dr. Anupama M. Hasija from Shahid Bhagat Singh Evening College, and today we are going to talk about river regimes and channel flows. The characteristic temporal patterns of river flows, quantity and variability is called as river regime. The flows of river varies on time scales of hours, days, seasons, years and longer. River regimes show geographical patterns mainly determined by river size, climate, geology, topography and land use, land cover. The river regime is defined by 5 critical components. They are magnitude, frequency, duration, timing and rate of change. Magnitude of discharge is the amount of water moving past a fixed location per unit time. Magnitude can be referred to as either absolute or relative. Maximum and minimum flow magnitudes of flow vary with climate and watershed size. The frequency refers to how often a flow above a given magnitude recurs over some specified time interval. The duration is the period of time associated with specific flow conditions like floods. The timing of flows of defined magnitude refers to regularity with which they occur. The rate of change or flashiness refers to how quickly flow changes from one magnitude to another. Now let's discuss the classification of river regimes. There are 3 basic types of regimes. Number 1, simple regime, in which one maximum and one minimum per year. Secondly, mixed regime or double regime, 2 maximums and 2 minimums per year. Thirdly, complex mode, which has several extremes. The simple regimes can be further classified in nival, pluvial or glacial depending on the origin of the water. Simple river regimes. Glacial river regimes. The glacial river regime is characterized by very high discharge during summer season due to ice melt and very low discharge from the end of autumn to early spring. The amplitude of monthly variation of discharge is greater than 25. In glacial regime, very high daily variability in discharge is found during the year. Mostly such regimes are found at high altitudes above 2500 meters. Nival. Snowmelt dominated or nival regimes occur in the interior plateau and mountain regions and in higher elevation zones of coast mountains. In these zones, winter precipitation dominantly falls as snow and remains in storage until spring melt. As a result, these regimes exhibit low flows through winter and high flows in May, June and July. The nival regime is similar to the glacial but attenuated, and the maximum takes place earlier in June. The plain nival regimes have short and violent flood in April to May following massive spring thawing of winter snows. Pluvial. The pluvial regime is characterized by high water in winter and spring along with low discharge in summer. There is a greater interannual variability in discharge. Flow is generally rather weak. It is typical of rivers at low to moderate altitude from 5000 to 1000 meters or 1600 to 3300 feet, tropical pluvial. The tropical pluvial regime is characterized by low discharge in cold season and abundant rainfall in warm seasons. and minimum can reach very low values. There is great variability of discharge during the year. Mixed regimes or double regime, Nevoglacial. There is one true maximum in Nevoglacial regime which occurs in late spring or early summer, that is from May to July in case of northern hemisphere. Relatively diurnal variations during the hot season are noticed with significant yearly variation, but less than in the snow regime. Nevopluvial. In this type of river regime, two maximums occur, the first occurring in the spring and the other in the autumn. A main low water is observed in October and a secondary low water in January. Significant interannual variations are found in the discharge. Now, what is pluvio-neval? The river regime has a period of rainfall in late autumn due to abundant rainfall, followed by a light increase due to snow melt in early spring. The single minimum occurs in autumn and the amplitude is low. Now we come to complex regimes. The complex regime is characteristic of large rivers, flow of which is diversely influenced by numerous tributaries from different altitudes, climates, etc. The influences diminish extreme discharges and increase the regularity of mean monthly discharge from upstream and downstream. Hydraulic processes and the flow regime. All rivers flow derives ultimately from precipitation, but in any given time and place a river's flow is derived from some combination of surface water, soil water and groundwater. Climate, geology, topography, soils and vegetation help to determine both the supply of water and the pathways by which precipitation reaches a channel. The different water movement pathways in different settings have different flow regimes. That is, why flow is variable in virtually all rivers? Collectively, overland and shallow subsurface flow pathways create hydrograph peaks, which are the river's response to storm events. By contrast, deeper groundwater pathways are responsible for base flow, the form of delivery during periods of little rainfall, variability in intensity, timing and duration of precipitation, either rain or snow, and in the effect of terrain, soil texture and plant evapotranspiration on the hydrological cycle combine to create local and regional flow patterns. The natural flow regime organizes and defines river ecosystems. In rivers, the physical structure of environment and thus of the habitat is defined largely by physical processes, especially the movement of water and sediment within the channel and between the channel and floodplain. To understand biodiversity, production and sustainability of river ecosystems, it is necessary to appreciate the central organizing role played by dynamically varying physical environment. The physical habitat of a river includes sediment size and heterogeneity, channel and floodplain morphology and other geomorphic features. These features are formed when the available sediment, woody debris and other transportable materials are moved and deposited by the flow. Open channel flows are those that are not entirely included within rigid boundaries. A part of the flow is in contract with nothing at all. In other words, the flow in an open channel or in a closed conduit having a free surface is referred to as free surface flow or open channel flow. Water travels downhill from points of higher energy to points of lower energy, unless forced to do otherwise, until it reaches a point of equilibrium such as ocean. This tendency is facilitated by the presence of natural conveyance channels such as brooks, streams and rivers. The water's journey may also be aided by man-made structures such as drainage swales, pipes, culverts and canals. Hydraulic concepts can be applied equally to man-made structures and natural features. The term area refers to the cross-sectional area of flow within a channel. When a channel has a consistent cross-sectional shape, slope and roughness, it is called a prismatic channel. If the flow is in a conveyance section is open to the atmosphere, such as in a culvert flowing partially full or in a river, it is said to be open channel of free surface flow. If a channel is flowing completely full with a water distribution pipe, it is said to be operating under full flow conditions. Pressure flow is a special type of full flow in which forces on the fluid cause it to push against the top of the channel as well as the bottom and sides. These forces may result from, for example, the weight of a column of water in a backed up sewer manhole or elevated storage tank. A section's wetted perimeter is defined as a portion of the channel in contact with the flowing fluid. Now, what is the open channel geometry? Hydraulic radius here means hydraulic mean depth, which is referred to as R. The hydraulic radius is defined as the flow area divided by wetted perimeter, and hydraulic depth is defined as the flow area divided by the top water surface width, where R is the flow area, meaning cross-sectional area of the flow. Wetted perimeter is P, meaning the length of the channel cross-section in the contact with the fluid, where the average depth is hydraulic average depth is Y, and the Y average is equal to flow area, meaning cross-sectional area of the flow. Top width is referred to as B, meaning width of the channel at the free surface. Now, to remember, depth of the flow was Y, vertical distance from the bottom to the surface. Top width B, the width of the channel at the free surface. Flow area is referred to as A, cross-sectional area of the flow, and wetted perimeter, which is referred to as P, the length of the channel cross-section in contact with the fluid. Based on different criteria, free surface flows may be classified into various types, which are steady and unsteady flows. If the flow velocity at a given point does not change with respect to time, then the flow is called steady flow. However, if the flow velocity at a given location changes with respect to time, then the flow is called unsteady flow. It is possible in some situations to transform unsteady flow into steady flow by having coordinates with respect to a moving reference. Typical example of such a situation is the movement of flood wave in a natural channel, where the shape of the wave is modified as it propagates in the channel. Now, uniform and non-uniform flows. If the flow velocity at a given instant of time does not vary within a given length of channel, then the flow is called uniform flow. However, if the flow velocity at a given time varies with respect to distance, then the flow is called non-uniform flow or varied flow. Depending upon the rate of variation with respect to distance, flows may be classified as gradually varied flow or rapidly varied flow. Now, what is laminar and turbulent flow? The flow is called laminar flow if the liquid particles appear to move in a definite smooth path and the flow appears to be as a movement of thin layers of top of each other. In turbulent flow, the liquid particles move in irregular paths which are not fixed with respect to either time or space. Now, what is the relative magnitude of viscous and inertial forces? This determines whether the flow is laminar or turbulent. The flow is laminar if the viscous forces dominate, and the flow is turbulent if the inertial forces dominate. The ratio of viscous and inertial forces is defined as Reynolds number, which is denoted as Re, is equal to VL. Here Re is Reynolds number and V is mean flow velocity and L is a characteristic length and the small v is kinetic viscosity of the liquid. Hydraulic radius may be used as a characteristic length in free surface flows. Now, the flows of three types are subcritical, supercritical and critical. A flow is called critical if the flow velocity is equal to the velocity of a gravity wave having small amplitude. A gravity wave may be produced by a change in the flow depth. The flow is called subcritical flow if the flow velocity is less than the critical velocity, and the flow is called supercritical if the flow velocity is greater than the critical velocity. The Froude number, which is referred to as Fr, is equal to the ratio of inertial and gravitational forces, and for a rectangular channel it is defined as Fr is equal to V under root dy, where y is the flow depth. Depending upon the value of Fr, flow is classified as subcritical if Fr is less than 1, critical if Fr is equal to 1 and supercritical if Fr is more than 1. Now, let us come to the pressure distribution. The pressure distribution in a channel section depends upon the flow conditions. Let us consider several possible cases starting with the simplest one and then proceeding progressively to more complex situations. Static conditions. Let us consider a column of liquid having cross-sectional area delta A. The horizontal and vertical components of the resultant force acting on the liquid column are 0, since the liquid is stationary. So, if P, that is pressure intensity at the bottom of the liquid column, then the force due to the pressure at the bottom of the column acting vertically upwards is P delta A. The weight of liquid column acting vertically downwards is the correlation between Gy delta A. Since the vertical component of the resultant force is 0, we can write P delta A is equal to the correlation of G and Y delta A, or P is equal to the correlation of G and Y. In other words, the pressure intensity is directly proportional to the depth below the free surface. Since correlation is constant for typical engineering applications, the relationship between the pressure intensity and depth plots as a straight line, and the liquid rises to the level of free surface in a piezometer. The linear relationship based on assumption that correlation is constant is usually valid except at very large depths. where large pressure results in increased density. Horizontal parallel flow. Let us now consider the forces acting on a vertical column of liquid flowing in a horizontal frictionless channel. Let us assume that there is no acceleration in the direction of flow and the flow velocity is parallel to the channel bottom and is uniform over the channel section. Thus, the streamlines are parallel to the channel bottom. Since there is no acceleration in the direction, the component of resultant force in this direction is 0. Referring to free body diagram and noting that the vertical component of the resultant force acting on the column of liquid is 0. We may write correlation of G and Y delta A is equal to P delta A, or P is equal to correlation of G and Y, or Y and Y, in which Y is equal to correlation of G is equal to specific weight of the liquid. Note that this pressure distribution is the same as if the liquid were stationary. It is therefore referred to as the hydrostatic pressure distribution. Parallel flow in sloping channels. Let us now consider the flow condition in a sloping channel such that there is no acceleration in the flow direction. The flow velocity is uniform at a channel cross section and is parallel to the channel bottom. That is, the streamlines are parallel to the channel bottom. The cross sectional area of column is delta A. If theta is equal to slope of channel bottom, then the component of the weight of column acting along the column is correlation of GD delta A cos theta, and the force acting at the bottom of the column is P delta A. There is no acceleration in a direction along the column length since the velocity is parallel to the channel bottom. Hence, we can write P delta A is equal to correlation of GD delta A cos theta, or P is equal to correlation of GD cos theta is equal to YD cos theta. By substituting D is equal to Y cos theta into this equation, where Y is the flow depth measured vertically, we obtain P is equal to YY cos theta 2. Now, that in this case, the pressure distribution is not hydrostatic in spite of the fact that we have parallel flow and there is no acceleration in the direction of flow. However, if the slope of channel bottom is small, then cos theta 1 and the correlation between D and Y exists. In several derivations, we assume that the slope of the channel bottom is small. With this assumption, the pressure distribution may be assumed to be hydrostatic if the streamlines are almost parallel and straight, and the flow depths measured vertically or normal to the channel bottom are approximately the same. Now, what is curvilinear flow? In the previous three cases, the streamlines were straight and parallel to the bottom. However, in several real life situations, the streamlines have pronounced curvature. To determine the pressure distribution in such flows, let us consider the forces acting in vertical direction on a column of liquid with cross-sectional area as delta A. If radius, which is denoted as small r, of curvature of the streamline and V is the flow velocity at the point under consideration, then centrifugal acceleration is equal to V to R, and centrifugal force is the correlation of Ys delta AV to R. Dividing the centrifugal force by the area of the column and converting the pressure to pressure head, we obtain the following expression for pressure head. YA. Acting at the bottom of the liquid column due to centrifugal acceleration, YA is equal to 1G Ys V2R. The pressure due to centrifugal force is in the same direction as a weight of column if the curvature is concave, and it is in a direction opposite to the weight if curvature is convex. Therefore, the total pressure head acting at the bottom of the column is algebraic sum of pressure due to centrifugal action and the weight of liquid, that is total pressure head, is equal to Ys. A positive sign is used if the streamline is concave and a negative sign is used if the streamline is convex. Thus, the liquid in a piezometer inserted in the flow rises. In other words, pressure increases due to the centrifugal action in concave flows and decreases in convex flows. The energy principle. Now, what it is? The first law of thermodynamics states that for any given system, the change in energy, that is delta E, is equal to the difference between heat transferred to the system Q and the work done by the system on its surroundings W during a given time interval. The energy referred to in this principle represents the total energy of the system, which is the sum of potential energy, kinetic energy and the internal molecular forms of energy such as electrical and chemical energy. Although internal energy may be significant for thermodynamic analysis, it is commonly neglected in hydraulical analysis because of its relatively small magnitude. In hydraulic applications, energy values are often converted into units of energy per unit weight, resulting in units of length. Using these lengths equivalents gives engineers a better feel for the resulting behavior of the system. When using these length equivalents, the engineer is expressing the energy of the system in terms of head. The energy at any point within a hydraulic system is often expressed in three parts. Pressure head. Pressure divided by specific weight, that is Y. Elevation head, that is Z. Velocity head V2 by 2G, where P is pressure, Y is specific weight, Z is elevation and V is velocity. The energy equation. In addition to the pressure head, elevation head and velocity head, energy may be added to a system by a pump and removed from the system by friction or other disturbances. These changes in energy are referred to as head gains and head losses. Because energy is conserved, the energy across the 2 points in the system must be balanced. This concept is demonstrated by energy equation, which says P1, which is pressure, is divided by Y, which is specific weight of the fluid, plus Z1, that is the elevation above a datum, plus V1, which is the fluid velocity, and its square, divided by 2G, that is gravitational acceleration, plus head gain, that is Hg, which is from a pump, is equal to pressure 2 divided by V plus Z2 plus V2 square divided by 2G, that is gravitational acceleration, plus HL, combined head loss. Now, what is hydraulic grade? The hydraulic grade is the sum of the pressure head P by Y and elevation head Z for open channel flow in which pressure head is 0. Hydraulic grade elevation is the same as a water surface elevation. For a pressure pipe, the hydraulic grade represents the height to which a water column would rise in a piezometer, which is a tube open to the atmosphere rising from the pipe. When the hydraulic grade is plotted as a profile along the length of conveyance section, it is referred to as a hydraulic grade line or HGL. Now, what is energy grade? The energy grade is the sum of hydraulic grade and velocity head, that is V2 by 2G, which is gravitational acceleration. This grade is the height to which a column of water would rise in a pilot tube, an apparatus similar to a piezometer, but also accounting for fluid velocity. When plotted in profile, this parameter is often referred to as the energy grade line or EGL. For a lake or reservoir in which the velocity is essentially zero, the EGL is equal to the HGL. Energy losses and gains, energy or head losses where HL in a system are due to a combination of several factors. The primary cause of energy loss is usually the internal friction between fluid particles traveling at different velocities. Secondary causes of energy loss are localized areas of increased turbulence and disruption of the streamlines, such as disruptions from valves, other fittings in a pressure pipe, or disruptions from a changing section shape in a river. The rate at which energy is lost along a given length of the channel is called the friction slope and usually represented as a unit less value or in units of length per length. Energy is generally added to a system with a device such as a pump. Now let us summarize. Here we used common term river regimes and channel flows. They were classified, defined using several different criteria, and the properties of a channel section were presented. The distribution of velocity and pressure in a channel section was discussed. The distribution of pressure was discussed and a brief description of energy principle and energy flow was presented to facilitate its application for further references. Thank you.